Hello my dear friends, hope all of you are doing well by keeping yourself safe. So today in this video I will discuss one interesting topic called the geometrical frustration and hope all of you will like it. So let's start. The topic is for today is geometrical frustration. Sometimes a little frustration can make life interesting. So this is the concept is true in physics also, where the frustration can lead to some desire or the peculiar properties of the material. The frustration refers to some forces that compete with each other but cannot be satisfied simultaneously. The concept is broadly used in magnetism, the negative thermal expansion of the solids. The negative thermal expansion means where some materials contract upon heating in constant pressure, like the Invar Fe3Pt, and SN 2.75 C60 is also alloy material, and also in the case for the soft materials. The soft materials are which can be easily deformed by thermal stresses or thermal fluctuations at the room temperature. So the concepts used in magnetism and negative thermal expansion of the solids and also for the soft materials. Studies of the frustration begins with antiferromagnets, where the frustration has a simple geometric origin, and this geometrical frustration occurs in system of spins on lattices involving triangular shapes or the logos. So you can see this is a 2D triangular lattice and this is for the individual one. So we can consider some antiferromagnet of the 2D structure for a triangular lattice where we cannot find all the neighboring spins are antiparallel to each other, and it is one of the prototype of the frustrated magnetism. So Wannier in 1950 showed this model has a large degeneracy in the ground state. So you can see in the figure in the left, it is a 2D triangular lattice where the spins in the lattice in angle due to with each other. You can see this is in this direction. If I consider one lattice, so the spins in this direction and these two are in this direction due to their neighboring interaction of the spins, and this effect is called quantum entanglement. If we consider one individual lattice, one individual triangle, if we consider, you can see that all the spins are centered in some specific direction. So you can see this is for the one individual triangular lattice, one individual triangular part. So these two are anti-parallel, but these two are parallel. So there are 6 degeneracy in the ground state, because you can see 6 different combinations. Considering one, like this one is up, this one is down, this one is down, but these two cannot be satisfied the relation that the neighboring spins are anti-parallel to each other for the triangular lattice. So instead of 2 ground state from the Ising symmetry, there are 6 ground state, and such degeneracies can persist in both 2D and the 3D lattices. Now if I consider for a square lattice, you can see that for a square lattice each spins can be aligned antiparallel with all its neighbor, but for a triangular lattice such configuration is impossible. You can see for a square lattice each spin can be aligned anti-parallel to each other, each neighboring spins, it is better to say. But for the triangular lattice, if this one is up, this one is down, I don't know what is the direction of this spin. If it's up, then these two are parallel. If it's down, then these two are parallel. So we can say that the system is frustrated. So again, from our previous knowledge, what we can say that the spin susceptibility of local moment it follows the Curie-Weiss law, and it is of the form the spin susceptibility has the relation chi is equal to C by T minus theta CW, where T is the absolute temperature and C is the Curie constant. And from the plot of 1 by chi, if I plot 1 by chi versus T, so we can get the natural estimate of the strength of the magnetic interaction from the value of the theta C omega. If I plot 1 by chi over T, we will get the value of the theta C omega, which gives the nature of the magnetic interaction. So from there we can get the information that theta CW less than 0 for an antiferromagnet, and the frustration parameter is defined as F is equal to theta of CW divided by Tc, where Tc is the Curie temperature. So what is the Curie temperature at which the magnetic ordering freezes? So now this is our next page, and this is some specific region where F is greater than in between 5 to 10. This is the frustration parameter, and it indicates the strong frustration causes the and due to the strong frustration, it causes the suppression of the ordering. Ordering means the magnetic ordering of the spin. And if T satisfies the relation that Tc less than T less than theta Cw, it defines the spin liquid regime. Now in triangular Ising antiferromagnet, the ground state entropy is extensive and equals to S0 is equal to 0.323 kbn, where n is the number of the spins. We have seen that this is the ground state entropy of this is the value S0 is equal to 0.323 kbn, where n is the number of the spins. At the low temperature, the spins continue to fluctuate thermally in a correlated manner, and they are restricted to ground state of Ising antiferromagnet and form cell liquid. This is called the spin liquid. The frustration parameter F is equal to infinity. It means that the spins remain liquid up to the temperature, absolute temperature T is equal to 0. So this is the parameter F is equal to infinity means. Now the frustrated magnets initially opens a new window to realize the new materials from their application part, the frustrated magnets. Now we can consider one setup model Hamiltonian for an interaction between the nearest neighbor. So we can write the Hamiltonian like H is equal to, in my last video of the exchange interaction I have discussed that J is called the exchange integral or the overlap integral. So for the nearest neighbor interaction we can write the Hamiltonian as J sum over I J Si dot Sj, where I and J are nearest to each other. So J is called the exchange or the overlap integral, and the spin can be taken as classical or the discrete model with S is equal to plus minus 1, or we can write spin as a 3 component of the Heisenberg vector. So the spin has a 3 component using the Heisenberg idea. So you can write it each other 3 component along the 3 direction in the space, that is Sx, Sy and Sz, with the value of mod of S vector. For some mutually interconnected spins, the Hamiltonian we can express the Hamiltonian for the mutually interconnected spins, where the resultant number of spins becomes the small q. So we can write the Hamiltonian as J is J divided by 2 sum over I is equal to 1 to q mod of Si square. And for the ground state, the total spin is 0, as I have already discussed. Now to maximize the ground state degeneracy for a fixed number of spins, we need to minimize the number of the constraints. Like in Kagome lattice, in this picture we will discuss that. And so this is the structure of the Kagome lattice. Again I am speaking. In Kagome lattice each side is belong to 2 different triangles, whereas in the less frustrated triangular lattice each side may have more than the 2 triangles. Some may have the 6 triangle like this. And in the case of 3D structure, that is called the pyrochlore lattice. So you can see the most degenerate and the more frustrated lattice is the one where the vertex is sharing the octahedra. So this is called the pyrochlore lattice. So this is in the 3D structure, this is the most degenerate and the more frustrated lattice. The ordering of the proton in the crystalline lattice, in the crystalline ice, is the first recognition of the significance of the geometrical frustration. So the ordering of the proton in the crystalline ice is one of the example of the geometrical frustration. So we can write it that in our next page, that the ordering of the proton in crystalline lattice is a recognition of the geometrical frustration. So out of the total number of the possible spin states, only the fraction is actually in the ground state, for which the total spins is sum up to 0. Now to find the ground state entropy, we first consider at the high temperature where the entropy is high, it means the ordering is the maximum. So due to the free spin we can write that at the high temperature the entropy due to the free spin, we can write that SF as the final entropy, that would be n kb times ln omega, where sigma is the number of the accessible states and n is the number of the spins, free spin. Now if I consider that delta is the amount of entropy that leaves the system as it cools to the temperature. So the ground state entropy, I mean at the lower temperature, what it will be? S0 is equal to SF minus of delta S. So if I subtract delta S from SF, I will get the ground state entropy. Now some example for the geometrically frustrated antiferromagnets. So what are the some material that shows this property of the geometrical frustration? So you can see that the material like SrGa3Cr9O19, it has the structure of the pyrochlore slab, and the theta Cw value is 515, that is in the Kelvin, and Tc the Curie temperature is 4 Kelvin. The one is the hydronium iron jarosite. So the jarosite is a hydrous sulfate material, including which includes the potassium and the iron. So it is the structure of the Kagome lattice that I have discussed, and it has a value of theta CW of 700 Kelvin and the TC value of 14 Kelvin. And the next one is the Y2MO2O7. MO means the molybdenum. This is also have the structure of pyrochlore, and theta CW value of 200 Kelvin, and the TC has the value of 22 Kelvin. So, as in the geometrically frustrated antiferromagnets, a lot of ground state degeneracy is possible, and the degeneracy is not due to the consequence of the symmetry. So, it is expected that the spectrum fluctuation around each ground state to be different. So, we are expecting that the spectrum will be different around each ground state. So, my friends, I am concluding my discussion here. Please do like, share and subscribe our channel Invisible Threads. Stay tuned and keep supporting us. Thank you.